We just evaluate how the first order system will respond to a unit step input, right? And then from there, previously we conclude that when time is equal to the time constant, then the response will be equal to 63.2% of the steady state value. Now, we are going to discuss on how a first order system will respond to unit impulse signal. Okay, let me pop up again this slide. So we have already discussed how the first order system will respond to step input. Now let's discuss how the first order system will respond to impulse input. As you know, impulse input looks like this. So impulse signal is just 0 all over the time, except when time is equal to 0, the value is infinite. Okay, so impulse signal is like this. In Laplace domain, impulse signal is equal to 1. So when you want to find the unit impulse response of your first order system, then basically you just have to multiply the transfer function with the impulse signal in Laplace domain, which is 1. So the response in this case will be equal to the transfer function times 1, which is the transfer function itself. I have to mention here, let's consider again a simple first order system where the DC gain K is equal to 1. So let's take a case only when K equal to 1. So we only have one parameter, which is the time constant T here. Having the response in Laplace domain, of course, you can evaluate the response to time domain. Just refer to your Laplace table, and the response in time domain will be like this. If I plot the response in time domain, the one that we just derived in the previous slide, the response will be like this. This is the response in time domain. What does it mean? When time is equal to 0, the response is equal to 1 over t. So it's just the inverse of the time constant. But when the time is equal to the time constant, the response will be equal to 0.37 of the initial value. Same thing, when time is equal to 3 times of the time constant, the height here will be equal to 0.05 of the initial value of this. So by looking at the impulse response, same like referring to the unit step response, you should be able to identify the time constant of your system. Let's consider again the previous case when we are evaluating a unit step response. So if you have a system, you know that the system is a first order system. You want to identify the time constant of that system. So how you will do that? You just give a unit step input to the system, and then you look at the response. The time when the response is equal to 63.2% of the steady state value, that time, the time is equal to the time constant. So that's how to identify the time constant of the first order system using step input. Similarly, you can also identify the time constant of your first order system using unit impulse signal. You give an unit impulse signal to the first order system, and then you look at the response. The time when the response is equal to 37% of the initial value, that time, the time is equal to the time constant. So it's pretty similar, just the way how you see the time constant will be slightly different in here, but both of them will work to identify the time constant. Now let's take a look how the first order system will respond to another signal. In particular, here we are going to talk about unit ramp response. You still remember what is unit ramp? Unit ramp is just a linear signal, like the one that you see on the right side here. So this is time. The response is increasingly linearly in time. So the slope here is equal to 1. So there is a unit ramp signal. This will be the third test signal that we can use to identify the parameter of the system, of our first order system. Let's take a simple case again, same like before. We take a first order system with the DC gain is equal to 1 here. So the transfer function of our first order system looks like this. Unit ramp in Laplace domain, if you refer to the Laplace table, will be equal to 1 over s squared. So the response again in Laplace domain will be equal to the transfer function times the ramp, unit ramp input in Laplace domain 1 over s squared. And then we will do the partial fraction expansion. This is the response that we will get in a Laplace domain. And then what next? Let's just inverse Laplace it using your Laplace table to time domain. After we inverse it, this will be the response, the unit ramp response in time domain. So let's try to plot it. We plot this response together with the unit ramp input. So the blue one that you see in this slide is the input, the unit ramp input. And if you plot the response that we just evaluated, the response will look like this. The black one. So the black one is the unit ramp response. In steady state condition, the slope of the response, this slope, is exactly will be equal to the slope of the input. In our case here, since we have a unit ramp input, so the slope here is 1. The slope of the response in steady state condition will also be equal to 1. So if the slopes of these two signal, the input and the output are the same, so you will have a constant error. What I mean by error here is the difference between the input and the output. The error will be constant. And how to identify the time constant of your first order system using this unit ramp response? Apparently, the time constant will be equal to the distance between the input and the output in steady state condition. So this distance will be equal to the time constant, or it is also equal to this distance. So this distance, or basically is this distance, the steady state error is your time constant. Okay, so that's how to identify a time constant of a first order system using a unit ramp signal. So you have already evaluated now how to identify the time constant of a first order system using 3 different test signal. The first one is the step signal. We did it also for the impulse signal, and this one we did it using a ramp signal. So to conclude again, for a unit ramp response case, the larger the time, so when time approaches infinity, when time is going to the steady state condition, the error will be constant and the error will be equal to the time constant. So again, using unit ramp testing, you just let it run, wait for a few seconds, few minutes until the steady state condition is reached, and you just measure the difference between the input and the output, and that will show you the time constant. Now let's consider a case when the response as well as the input is representing a position or the displacement of your system. Smaller time constant means you will have a smaller steady state position error. What I mean by steady state position error, what I mean by position error is the difference between input and output. And if input and output, the RT and CT represent the position, so the difference basically is the position error. And if RT, the ramp signal, represent the position, so the slope of RT basically is the velocity, right? Slope of the position signal, the first derivative of position signal basically is the velocity. The first derivative of position is velocity, right? So if RT is position again, there will be no velocity error. What do I mean by no velocity error? That means the velocity of the input RT and the velocity of the response CT will be the same. What is velocity again? Velocity is the gradient, is the slope. So the gradient of the RT and the gradient of the CT will be the same when the steady state condition is reached.